Okay, welcome back everybody to the ML machine learning microcourse from Kaggle. This is part, I think, 4. Is about the validating the model. On the previous session, we already built the model, which means what means by model is basically a mathematical function that the machine or the computer generates. By learning the data from, right? If you recall, what's the difference between the traditional software programming approach and the machine learning? The traditional software programming is basically the human is the one making the mathematical instructions or making the mathematical functions or making the instructions step by step, if then else, looping and all that stuff while we're doing this, doing that. In the machine learning model, we ask the machines to do that mathematical functions or basically writing the instruction set on its own based on the data that we provide. So we are now in the we already built the model, right? And we have this called the idea of a training set and the test set. I will show you just 1 second. So there's a training.csv. This is where we use the data uh, used to train the model. And then now after the model is trained, we want, before we can deploy it in the real world, we want to test it. We want to validate if the model is really good or suck, right? If it sucked, then you want to go back to the drawing board again. Um, try to There's this idea of overfitting and underfitting in the machine learning world. Then you want to tweak the model in such a way, and it's called that process of tweaking. I think there's a name called, I think it's called regularization, right? And that's another topic in more advanced courses. So right now we are just concerned whether the model is good enough or not. Okay, the term here is good enough or not in quote, right? In other words, whether it's overfitting or underfitting. In other words, also it's a generalized model. So in the machine learning world, there's so many buzzwords. So you just want to understand all of these buzzwords, right? But the idea is, if the model is good enough for the world, it doesn't predict something like stupid, like, right? So people can make a stupid decision, right? We want the model to be like more or less like capture what's happening in the real world, right? What's happening to solve real world problems, right? Uh, it doesn't matter if you're how complex your model, if it doesn't like solve the real problem in the real world, then your model is sucks. Then you want to go back to the drawing board and retrain all of this model, right? So that's what the technology is for. Technology is to help human being, right? To make a better place, right? So anyway, I'm going off tangent right now. So we are going to validate the model. In order to validate the model, we are introducing another concept, which is called a test.csv. This is kind of like the you separate the data that you have, that you want to train the model, into kind of two. So in machine learning and in sklearn, there's you can split the data automatically by like 80 to 20, something like that, or 70 by 30. But basically, the idea is to break down the data into two. One for training and one is for testing, and they are not overlapping. The idea is you want to be independent, right? So if you want to use the test data, you don't want the test data is the same as the training data. Otherwise, what's the use of it, right? You want to completely like different, so you want to gauge. The idea is to gauge, do you have an idea if your model is good enough or not? Even after you test it, the model, even if it says the model is kind of a good in quote, right? You still have that this kind of mentality of a kind of prejudice that is it really good? What happens if my whole like training data and the testing data is like still sucks, right? It's still like the idea you heard about this like a bias data. So before you even like want to put all of the data in the into the training or into the test, you want to make sure the data is representable. It's like, it's not biased and all that stuff, right? Good stuff. So, and that's itself is kind of like another topic, right? How do you want like, and that's like we can discuss it like this but like what is the good way to do that. Anyway, so right now we are here. So to recap, um, blah blah blah, we already built the model. In this exercise you will test how good your model is, and we're gonna run this cell below to set up our coding environment. This is just like a precursor. So basically what we are doing here again is importing pandas as PD, and then we are importing one of the library from the sklearn.tree. um, it's called decision tree. This is one of the algorithm that we are using. Again, in machine learning, there's so many different kind of algorithm. There's a support factor machine, there's decision tree regressor, there's even probably ordinary decision tree. There's a list, probably like a list square method. There is a uh, ordinary list square method. This random forest tree. There is a XGBoost. There is a this millions kind of different algorithm that you can choose from. Right? And then that's the idea of the machine. As a machine learning engineer, you have to know like what tools or what algorithm you use for what to solve a specific use case, right? And that's kind of the hardest part, right? Um, but having said that, there's amazing one just one branches of algorithm that like rule them all. Have you watched the ring? It's like one ring to rule them all. Then this algorithm is called deep learning. But the disadvantage of deep learning, at least in general, in theory, that you have tons and tons of data as compared to the machine learning model. You can just go ahead and just train your model using just a little bit of data, and you're fine. But again, there's a caveat on that. Again, I'm just going off tangent here. There's in deep learning, there's a thing called transfer learning, where the idea is you already transfer. I'm sorry, you already train the model using tons of data, and then you can just use that model and to reuse it to train for a different use case. So anyway, so we are going to use the train.csv here. We are using the output is a sale price, and then we are picking all of the seven, I think it was seven different features, lot area year built, right? Um, and then we are putting the algorithm into the model, and then we are fitting it, right, with X and Y. So this is where you train the model, where you find the parameters. If you remember your high school algebra is y equals to mx plus b. Um, running this code is basically you're finding the m and you're finding the b. You're finding basically the parameter, whether it's y equals to 6x plus 7 or y equals to 10x plus minus 7 and so on, right? Um, this is all about you're just finding the hyperparameters for that particular model that you choose. Um, and then we're gonna print the prediction. So we're gonna put the prediction for the first five data set. Yeah. So dot hat is the first five. Um, and then you are going to print the actual output, also the first five, right? And then after that, we're gonna check. This is just to check whether it's correct or not. Okay, so we're gonna run this model, see what's gonna happen. So if you can see here, this is the output. I'm just gonna make it this smaller so you can see better. Oh, yeah, I think that's better, right? So the output on the prediction, it's this one, which is exactly the same as the actual output. Why is that, right? You want to know why? Well, it's kind of obvious because we are using still the training data. We are using this for both the prediction and to print out the real output from the train.csv. So now we want to split the data into train and test. So okay, so we are going. I think we're going to import that, and then we going to use random state equals to 1. Um, okay, so this is the code to do that. So you get it from the sklearn .model.selection. You are going to import that particular uh, function to speak or method, right? And then we are going to put the value into the train X, validation X, and train Y and validation Y. Um, we're putting inside that library is the X, right? Which is the from the training data, which consists all of the features that you think is important, and then you get the output to the Y, and then you because you want it to be reproducible, then you want to make um, qualifier here random set equals to 1, or you can use that equals to 2, but over here it's asking for random set equals to 1, right? And then let's run this one. It says correct, so that's good. And then this is just going to print the solution, which is kind of the same as the one that we did on the previous one. It's exactly the same. That's good. And then step 2, we are going to specify and fit the model. So we are going to create the decision tree regression model and fit it into the relevant data. So this is the first line of code, right? We put also random state equals to 1. And then we are going to fit the model, right? Using the only the train X and train Y. So remember the difference here, if you can go back up here, when we fit the model here, right, using dot fit, right, we are basically putting all of uh, the, the data from the X, and the X is basically from the home data, right? Right. But over here, the difference is you are just getting the train X, right? Over here, right? So you're just getting um, you're because you're already splitting the data into just train and test. So in order to train to fit, we are just using the training part. Okay, and then we're just gonna run this. Hmm. I wonder why is it doing this? This is kind of weird. Okay, it's not supposed to print. I'm not sure why is it printing. Okay. Anyway, so okay, so just solution is the same, and then we're gonna make prediction with validation data. So we just use dot predict validation X, right? And then that's the solution. Okay, and then inspect your prediction and actual values from validation data, and then we're gonna print the failed prediction, and then we are gonna compare it with the y hat over here. If you look at the first five, um, 186, 184, oh, not sure about this. Um, I think you can just print the, let me see, predict dot hat 2. Let's see. Yeah, you can do this. So predict dot hat. So um, I think you can do this like dot hat. Nope, you cannot do it from there. Okay, fine. Um, you can do it, I think, from not from the print, but from the where is the prediction? Oh, dot predict. Yeah, IO model dot predict. Okay. Okay, got it. IY model predict. Um, IY model predict. Something like this. Okay. Let me just. Okay, I just want to see how it's being constructed. Okay, I think you can do this. I think you can just copy this, um, and then you can do this, and then you can dot head. Just, yeah, I think, yeah, it's the same. So if you can see here, the prediction now it's not the same, right? Because the prediction you're using the test validation X because you're basically splitting this one. This is the prediction from the split data from the train and test data. While the Y hat is still the whole the whole thing, right? It's not being split. That's why there's a difference. Okay. So what do you notice that is a different from what you saw in sample prediction, which are printed after the top code cell? Do you remember why validation prediction differ from in sample? This is from the calculate the mean absolute error in the mean validation data. Okay. Um. So okay. Let me go cheat sheet here. Mean absolute error. So this one, the value y, the value y, validation y. So it's I think validation y. Is that validation y? Yeah, there's a validation y um, minus um, just gonna copy this. Okay, I think this is easier. Yeah, I think it's like that. Um, File prediction. Yeah, I think it's the same. And then I'm just gonna print this, invalid syntax. I'm not sure. Oh, okay. This one. Okay, so it's correct. So this is the differences, the means absolute error. Okay, and then we're gonna check the solution, which is basically the same. You can you can actually exchange this. It doesn't matter because it's getting the absolute, right? minus become plus, and then plus become plus. So is that MA good? The mean absolute error. There isn't a general rule for what values are good that applies across applications, but close you. That's my coach basically. No, my editor. I'm supposed to make this one shot learning algorithm video. Anyway, so uh, there isn't a general rule what values are good and applies across applications, but you'll see how to use and improve this number in the next step. So um, that's for another video. If you want to learn more about underfitting and overfitting, which I already touch on like from the like overall in my like on my videos, that basically underfitting and overfitting is the idea that your model is not generalized, or your model is not good enough, the model is not good enough to be deployed in the real world, right? So you don't want to do that. You want to make sure your model is good enough and can solve real problem, and that's what the technology is for, right? Machine learning is to help human to make good predictions, so they cannot make decisions and bad decisions that have a repercussions, like like a domino effect that can cause like do harm than good in the society. All right, stay tuned on next for next session. I think part 5 on machine learning from Kaggle. We're going to discuss in detail more about underfitting and overfitting. Thanks for tuning in. I'll see you next time. Ciao.